All right, so welcome back to the second workshop in our series. And today we're going to be talking about an intro to MATLAB. So today we're going to do, if you have questions, use the Q&A feature and we'll respond to you there. And then also, if you want to respond to a question, you can just respond to everybody in chat. Or if you have a question specifically just for host and panelists for some reason, you can also just message host and panelists in the chat and we'll be sure to get to respond to that. And also tonight we'll be doing poll questions again. So if you want to answer a poll question, just put it in the chat. You can put it to everybody so everybody can see what everybody else is thinking. But with those kind of housekeeping things out of the way, I'll just mention one more time that this is being recorded. So if you aren't comfortable with that or you want to watch this again later, you can see the recording on YouTube. So I guess we'll get started with the session. So today, as I mentioned, we're talking about an intro to MATLAB. And MATLAB is a programming language designed for mathematicians. And everybody who has signed up for the webinar should have access to MATLAB Online, which is the tool that we'll be using. And you should have received an email when you registered with an access code to allow you to access MATLAB Online. But if you haven't set your account up yet or something, don't worry, I'll be sharing my screen and going through some code live during the session. So before we get into some of the more specifics of programming languages and some of the implementations of things in MATLAB, we'll do a little bit of a broad overview of what MATLAB is. So MATLAB is made by MathWorks, and it's a programming language designed for mathematicians. So pulling straight off of MATLAB's website, MATLAB is a programming platform designed specifically for engineers and scientists to analyze and design systems and products that transform our world. And the heart of the MATLAB language is a matrix-based language allowing the most natural expression of computational mathematics. So MATLAB is built for mathematicians and scientists, which makes it super great for modeling. And we won't have to worry too much about the matrix-based stuff today, but it just allows you to help scale things very nicely for math computations. So it's just something to keep in mind if you do continue to use MATLAB down the road. And then also millions of engineers and scientists worldwide use MATLAB for a range of applications. So not only will learning MATLAB help you in math competitions like the M3, but also in your future career as a mathematician or scientist, MATLAB will be useful because I know countless labs that I've encountered or I've seen MATLAB in workplace settings. So learning it now will give you a head start when you do go to do research or work in the career field of math and science. So that's kind of a high-level overview of what MATLAB is. But now we'll talk about some basic MATLAB programming notations. And these don't just apply to MATLAB, they apply to other programming languages as well. So first, the fundamental element of any computer programming language is it's going to run commands that we give the computer. And what the computer does is it runs these commands exactly as stated. So this means it's very important to understand what we are feeding into the computer. So when you type in code, you want to understand what you're writing and not just copy and paste things from the internet always, because if you don't understand what your code is doing, and then you're getting some sort of output that you don't fully understand, it could lead to wrong results or interpreting things wrong. And also note the computer does exactly what you type. So if you make a typo or something, the computer won't catch that and it'll probably spit out an error. And that's a big part of programming, is debugging those errors. Next, an important thing in programming languages is using comments. And comments are used to tell the computer which lines to ignore. So in MATLAB, you use a % symbol to tell the computer which lines are comments. And comments are very important because when you write a lot of code, you oftentimes will begin to forget what certain pieces do. So if you just leave yourself a little comment using English, you can quickly remember what that block of code does. And this is extremely useful when you're sharing code amongst people. So if you have a team for the M3 and you want to share your code around so that all your teammates can use it and run it, adding some comments in there will make it way more readable and way more usable for other people. And also, when you come back to your code in a couple of months, if there's good commenting on there, you'll be able to quickly remember what it does. So using comments is important in any computer language, and it's something we'll want to do as you continue forward with your coding. So the next main key part of a programming language and programming in MATLAB is that data is saved and kept track of as variables. And we'll talk a lot more about variables as they're kind of the fundamental building block of most of the stuff that we'll be doing tonight. But we'll see a lot more of those here soon. And then another interesting thing is that some languages are going to require that all lines of commands are run at once, and other languages will let you run commands one by one. And we'll be running commands one by one here tonight using MATLAB Online. And running commands one by one is super nice for things like math modeling, because you can change parameters, or if you have parameters that are dependent on functions, you can easily change inputs in those functions and just rerun those cells and not have to run the whole thing every single time. And it's great for debugging because if there's an error coming from one specific block of code, you can easily isolate it when running line by line. So that's just a nice thing that we'll get to see today. And then the final thing of programming notation is use tabs. So white space and indentation are very important. While MATLAB does not actually interpret the white space like some other programming languages like Python, it's still very important to include white space because it makes your code so much more readable. And even though it's not fully required in MATLAB, still putting those indentations is going to help you read your code and also understand what your code does without having to think too much. So we'll be using good white space, and that's something you'll want to do as well in your own coding. So now that we've talked a bit about some overarching programming notations, we'll talk about the tools we'll be using tonight and for this workshop. So this workshop uses MATLAB Online. And as I mentioned before, you should have a link to access MATLAB Online. And this will just be a quick poll question just to get an idea of who has their account set up. Just put in the chat if you have set up your MATLAB Online account with the link that you should have received. And no worries if you haven't, we'll be running the code live on my computer so that you guys can see what it looks like. But feel free to put in the chat if you have set up your account. Yes, using the app on your laptop should be fine if you have it downloaded. Cool. Great, it looks like a lot of people have set it up. If not, no worries, but it's something good to set up so you can run this code on your own afterwards. And then another thing to note is we have all of the code for all the sessions will be posted on MATLAB Drive. So if you want to access the code on your own and play around with things after the fact, or run the code along with me during the session today, you can feel free to click the link that was put in the chat to the MATLAB Drive where the code is held. So now we'll do a little bit about MATLAB Online. So MATLAB Online is a fantastic online tool for getting started with MATLAB because you don't have to download anything to your computer and you can run it all in the browser, which is super nice. And it's going to let you run MATLAB code one command at a time. And it's also going to save previous commands in an easy to work with format. So now I'll switch over to MATLAB Online on my laptop. And this is what MATLAB Online looks like. So as you can see, it's almost kind of something reminiscent of like a Microsoft Office Word kind of editor up top where you can like save and open new files. You have a whole bunch of different options for things that you can click through. And then you have your code down here, which is where we'll be editing and running code. And we'll talk a lot more about everything here, but it's nice in MATLAB Online, and we're using interactive notebooks here. You can also put some text inside of your code to help break things apart. But we'll be doing a lot more with this tonight, but this is just kind of what it looks like when you do run MATLAB Online on your computer. So continuing forward now, we'll start to talk a little bit more about fundamental building blocks of programming. And the first and most important thing we're going to talk about tonight is variables. And what variables are they're how your computer stores any and all information you will work with. So essentially variables are pretty names that you can give to memory addresses in your computer where you store information. So with that, the most important part of variables are their names. And there's some very specific convention in MATLAB and other programming languages around what you can name variables. So in MATLAB, variable names must start with a letter, and they can only contain letters, digits, and underscores. So you can't include any other symbols. So an example of a valid variable name is something like value underscore 5, because we're starting with a letter and we don't contain any illegal characters. And then an example of an invalid variable name would be something like 5 underscore value exclamation mark. And now just a quick chat question. Can anybody tell us why the variable name is invalid that says invalid on the screen? I'll give you guys a few seconds to think about that. Yes, I'll give it another few seconds. It looks like we have lots of good answers coming in. Yes, so the right answer is there's two different reasons this variable name is invalid. First is because it starts with a 5, and the second is that there's an exclamation mark, because both of those are not allowed in variable names, or you're not allowed to start with a 5 and you can't have the exclamation mark. And now just another chat question to get you guys thinking about variable names. If anybody wants to put in an example of another valid variable name You can pick whatever you want just to kind of get some more practice with this, because this is super important because you'll be naming lots of variables in your code. Yes, something simple just like X works. Yes. I'll give you guys another few seconds to put some more variable names in the chat. Yes, value 5 would work as well. Good names. Yes, these are all great variable names. And one other thing you want to think about when naming variables is you want to give your variable name something meaningful, because especially when you're writing complex programs with lots of variables, sometimes using undescriptive names can get confusing and you can lose track of what variables mean. So in general, when you're programming something, you're going to want to try and choose variable names that at least have some meaning to what the value of the variable actually is. But now we'll talk about some reasons why you can't include some variables in your names. So first, you can't use something like percent because, as we mentioned before, it's a comment. So if you put a percent in your variable name, MATLAB's going to interpret everything after the percent to be a comment, and you're not going to end up with a valid expression. You also can't use other symbols like the addition sign, multiplication, division, and so on, because these MATLAB characters are already reserved for special operations like addition and subtraction. So MATLAB's going to try and interpret those to mean their operations that MATLAB has predefined them to mean. And then lastly, you can't use things like parentheses, brackets, or curly braces because MATLAB uses those for other things, which we'll see here shortly. And the list would go on. But essentially, you can't use these terms because they already have meaning, and they would MATLAB would try and interpret the symbol to have meaning inside of your variable name, and you don't want that. So one last note before we switch over to some code is that variables have different types. And we'll talk a lot more about types after this slide, but you can check the type of variable by calling the function class. So now we'll switch over to code and see some variable name examples. So here we have our MATLAB code. And here we're defining first number to equal 16. And if we want to run this code, I've broken this code down into sections so that we can run it section by section. So we'll come up to the run section button. And if I click that, MATLAB has now defined first number to equal 16. And we know that it has because it's outputted first number equals 16 on the line below it. Now, sometimes you're not going to want MATLAB to output something like first number equals 16 because it's quite literally just a copy of the line that was above it. So if we do something like put a semicolon after, or if you do put a semicolon after the code, and now we rerun it, it won't output that variable that has been set to 16. So to suppress output in MATLAB, you put a semicolon. And this is just useful to know because sometimes you don't want it to output something, and you can just have it not output it by putting the semicolon. But now just to kind of show you that we can't define variables like we talked about. So if we try and put a 5 at the beginning, MATLAB's going to underline it, kind of like spell check of sort. And then if we hold over that, we can see that it's giving us an invalid MATLAB syntax. But then if for some reason we still try and run it, again, we'll get an invalid expression error. So MATLAB will tell you if your variable names are wrong, which is helpful. And then if we get rid of that and run it again, now we're back to it being a valid variable name. And now say you have suppressed the output, but you want to check the value of a variable, we can do something called display and then the variable name, and that will output the value of the variable. So if we run this block of code, we see we suppress the output from defining the variable, and then we display the variable value, and we see it outputs 9.100, which is just another helpful way if you ever need to check or print something to the screen, you can use DISP parentheses and what you want to display to the screen. And then the last thing, which will kind of segue us to our next part, we'll talk about class. So if we run this class function here, this should output double. So we're checking the class of our variable, which is double. And now we'll talk about what the different classes of variable in MATLAB are and what they mean and how we can use them to our advantage. So there's two main ways or types of numbers we can have. We can have integers and floats. And floats are just numbers that have decimals. So all numbers are going to be stored as one of these two types in MATLAB. So integers are used to store integers, as their name implies, and then floats are used to store numbers with decimals. And now in MATLAB, there are two different ways that you can store floats. The first is a double, and the double is the default value for all MATLAB numbers, no matter what. So if we think back to here, see 16 is an integer, so we've inputted an integer, but it still by default defines it as a double. And we'll talk about why MATLAB uses doubles in a second. But there's also another type of float we could use called singles. And the difference between a double, single, and an integer is obviously integers don't have decimals and take up less storage, but the difference between a double and a single is going to be the amount of storage space they take up. So doubles are going to offer the most precision, but take up the most storage. And doubles are good for numbers over 3.4 times 10 to the 38. So we have to have extremely large numbers for there to be essentially any difference in precision between variable types. And then singles are going to offer less precision, but only for those extremely large numbers, but they're going to take up less space in storage. So something to think about here is if your program in the future, we won't bump into this in our coding today, but in the future you have a program that it is taking up a lot of memory, you can think about switching your variable types from the default double to something else to take up less storage. But just remember, whenever you define a variable by default, it will be a double. So next, we're going to talk about some operations that can be done to combine integers and floats. So we have the whole array of standard arithmetic operations at our disposal. So things like addition, multiplication, subtraction, division, all those signs would do exactly what you would anticipate them to do. And we'll do some examples here in a second. And we also have things like modular arithmetic. So mod AB is going to return just the remainder if we were to divide those two numbers. And then lastly, the thing we'll talk about is round. So there's some built-in rounding functions, which can be super useful if you're dealing with significant figures and such inside of MATLAB. So we'll now switch over to MATLAB code again. So we'll come back to round, but first we're going to do some basic operations with variables. So in this cell here, we're just going to define two variables that we're going to use. So if we run this section, we'll then have them defined. So it ran, and now we'll come down to the next tab. So here we're subtracting first number minus number 5. So if we look up here, we're taking 16.1 and subtracting 5 from it. So we'd expect that to output 11.1. And if we run it, we see that is what it outputs. So then we can come down here to this cell. And what we're doing here is we have first number equal to itself plus 1. So this is kind of a really nice way to increment variables in MATLAB and other coding languages. So you can set a variable equal to its previous value plus some numbers. So just as a quick chat question, what do you guys think once we run the cell first number will be equal to? And note, we've defined what first number is initially equal to up here. So I'll give you guys a second to think about that. Yes, looks like we have a couple answers coming in. So we would expect it when we run it to put equal to 17.1 because again, we've just added 1 to the 16.1 up here. So thank you guys for answering. And now the nice thing is if we continue to run this cell, it will continue to increase that value by 1. So if we run it again, now it's 18 and 19 and then 20 and so on. And just note, we don't have to add 1. We could add anything to it. So we could add 5 or we could add another variable to it. So if we run that, then it's 25. But this will be super useful here in a second when we start doing loops and things like that. So that's just something you want to keep in mind. But we can also do division using the divide sign, and we can see it outputs 5.025, which is what we expect now that we've changed the value of first number. And we can do modular arithmetic as defined, where we have the two numbers, and if we run it, that should just output the remainder. And then lastly, you can use the caret to raise things to powers. So here we're raising first number to the number 5. And it outputs a very large number. And also note, you don't have to use variable names if you don't want to. If you just need to do a quick calculation for some reason in MATLAB, you can just type in the numbers with the proper sign. So here we're raising 23 to the 5th power, and we run that and it quickly puts out the answer. So those are just some basic arithmetic operations. And if you're ever confused about what a symbol is, just Google is going to be your best friend because there's great documentation for MATLAB out there. So just search it up and you'll quickly see what numbers or what symbols are available and what symbols are available and what they define. So now we'll take a second and talk about the round function. So the round function in MATLAB takes in a number, and then that's the only input you have to put in, but then we'll talk about some optional inputs in a second. So by default, if you put in a number, it'll just round it to the whole number part. So as you can see, we put in 29.123 and it just outputs 29. But then if you want to include some other options, we can put the number of decimal places we want to round it to. So say we want to round this to 1 decimal place, we could put in a 1 and then run that section again, and we get 29.1, which is what we'd expect if we round that to 1 decimal place. But note, if we put something like a 6 here, so it should round up. So now we should get 29.2, and we get 29.2. And you can also put calculations right into the rounding function. So here we have 0.1 plus 0.2222 rounded to 2 decimal places. So if we run that, we should expect to get out 0.32, and that is what we get out. So if you want a calculation and you know you only want it to a certain number of significant figures, you can round it as soon as the calculation is done without having to assign it to a variable name or something. And then the last thing we'll talk about with rounding numbers is significant figures. So MATLAB's round function has a really nice option where if you put as a third argument into your function, in quotes, you put significant, it'll round based on significant figures. So now it's rounding this very large number to 2 significant figures. So if we run that section, it rounds it to 2 significant figures for us. So these are just nice things to know about, because if you are dealing with significant figures or you need to round a number to the whole number part, there's built-in functions, so you don't have to worry about trying to write that code on your own. But now we'll switch back to our slides and keep talking about other data types. So now we've talked about numbers, but what about words in other format or words in text that we want to display? And in MATLAB, we're going to use string variable types for those. So strings are used to store words in text. And you can do something called indexing string, since a string is going to have a length based on the number of characters inside of it. So if you want to extract a part of a string, you can do that in MATLAB. So how you define a string is you're going to have a variable name using the same naming conventions as we talked about earlier. And then you're going to have equals, and then you're going to use the quotation marks and type in the text that you want to be part of your string. So here we have test string equals, this is a test, period. So now if we wanted to access specific characters of the string, we could use this function called extract. So if we do extract test string, and then, so that's our variable name that we're extracting from, and then the character or the index that we want from the string, which is 1 in our case. So if we run extract test string of 1, that would output the capital T, which is the first character in the string. And now one important thing to note, if you are familiar with another coding language like Python, is MATLAB indexing starts at 1, whereas a lot of other languages starts at 0. So if you are switching between languages, just note that string indexing starts at 1 in MATLAB. And then just another example, if we extract test string of 6, that would return the 6th character. And now we'll go look at some examples of strings. So we're going to do the classic hello world example, which is kind of a classic for getting started with programming languages. So here we're going to define test string to be equal to hello world. And then again, we're going to use the semicolon so that it doesn't output anything right away. And then we're just going to print the value of test string to the screen. So if we run this section, it prints hello world to the screen. And then, as we mentioned before, we can use the class to check a variable type. So if we run this section, which should output string, and it does. So we now know test string is a string type variable. And now we can use extract to get certain characters from the string. So just to check and make sure this is somewhat making sense, as a poll question, what do we expect this extract test string comma 1 to output after we run it? And I'll give you guys a few seconds to answer that in the chat. Give it another few seconds here, and then we'll run the cell. Yes, so if we run the cell, we should expect it to output a capital H, because that's the first character in our string. So lots of you guys got it, so great job. And then if we want to show that 0 indexing doesn't work, so if we try and put a 0 in here and we run this cell, we'll see that that's going to give us an error because numeric positions in MATLAB must be a positive integer. So just keep that in mind if you are familiar with another coding language when you switch over to MATLAB. And then we'll do another example. So here we're going to extract the 7th character from the string, which should be W. So if we run it, we get W. So strings are super helpful for printing words and things to the screen when running command or when running code. So now we'll move on and talk about the last big type or major variable type that we'll talk about today, and that's Booleans. So Booleans store truth values, and they can only be 2 values. They can be either true or false. So note, when you do assign a Boolean value of true or false, MATLAB's going to interpret that as 0 if it's false or a 1 if it's true. So Booleans aren't necessarily particularly useful in their own right, just by themselves, because they can only take on 2 values, but they're going to be fundamental for if-else statements and control flow in logic, as we'll see. So to define a Boolean, we'll switch right over to code. You have your variable name equals, and then you do true or false. And note in MATLAB, true is with the lowercase t and false is with the lowercase f. So that's the only way you can do it. So if I try it, I'll run this code first to show you that it successfully runs. But then if we try and put a capital T in here, it will error out. So be careful with capitalization because it does matter. As you can see, it does not recognize the capital T. So we run it again. And now we see when we do that, it's going to output that test bool is a logical variable. So that's the type. And then that its value is 1, which corresponds to true. And then we just show you real quick, if we change this value to false, it should output 0. And it does. So that's just how you define some basic Boolean operators. So now if we have it display test bool, remember we just assigned it to false, it'll print out a 0. So that's just something to note. When you do call the value of a logical operator, it'll be a 0 or 1 instead of actually printing out true or false. And then we can check the class of the variable. So if we run that, we see it outputs logical because that's the type of variable we're dealing with. So now we'll see how Booleans are actually useful and when they're outputted by MATLAB. So here we have a pretty simple expression. So we're defining x equals to 5. And then we're asking MATLAB to tell us what happens when, or is x greater than 7? So if we run this with x equal to 5, obviously we'll expect this to output false because x will not be greater than 7. So we run it and it outputs 0 just as we would expect. So that's kind of how MATLAB uses logical operators to actually do logic. So now just a quick poll question for you guys. We have this inequality here, x is greater than 7, and we're defining x. So how would we make this output true? And I'll give you guys a couple seconds to answer that in the chat. Yes, so lots of great answers. So there's 2 different ways we could do this, or 2 main ways we could do this. First, we could switch, flip it from a greater than to a less than sign. So now if we run this, it will output true. Or if we flip it back, we can change the value of x to something greater than 7, and it should also output true. So we change it to like 8, and then run that section again. We see it also outputs true. So those are just some very basic logical operations with Booleans. So if we now switch back to the slides, and we'll talk about some more useful ways to use Booleans. So if-else statements are going to be ways to actually check whether conditions are true, and then depending on if conditions are true, run certain code blocks. So there's 3 main ways we can use if-else statements. The first way will be just to test one condition. So here we have if condition, do a block of code, and then we'll end the code block. And then if you have like a catch-all statement, so if a condition isn't true, we want to do something else. We can do something like if condition is true, then we'll do this block. Otherwise, we'll do this default thing, and then we'll also need an end because MATLAB likes that syntax. And then finally, if we have multiple conditions we want to check, we can have if condition 1, do something, else if condition 2, do something, and we can have as many else if blocks as we need to meet all the logical conditions that we need. And then again, we can have a catch-all with the else block. So if all the conditions are not satisfied, we'll do something default. So these are the 3 main kind of logical or flows of logic of sorts in MATLAB. So now we'll switch over to code and see some examples of these. So the first if-else example, I'll kind of walk us through. So here we're defining x to equal 1. And then we have our first if statement. So we have if, and then we're checking this condition. So remember, MATLAB can interpret 1s and 0s as true and false. So if x equals true, and remember true corresponds to 1, then we'll display 1 equals true, and then else if x equals false, or x equals 0, display 0 equals false, and then we'll have an end. So here we don't have a catch-all case with an else, and because that's not necessary in this case. So thinking back to our knowledge of logical operators, we know if x equals 1, that should correspond to true. So with this statement, we would expect it to display 1 equals true. So if we run this section, it'll output 1 equals true. But now what if we change this to something like 8 or something, a completely random number that isn't going to do this? Nothing should be outputted when we run it. So we run it and nothing is outputted because x equals 8 does not meet any of these conditions. So nothing is outputted to the screen. So now we'll do another example of an if-else statement, but I'll have you guys think about this one in the chat. So here we have an x equals 11, and then we're going to do some logical operators asking stuff about x. So I have two questions. First, when we run this block of code, what is going to be outputted to the screen? And then the second question is, what essentially is this code telling us about x, or actually telling us about the variable? So I'll give you guys a couple minutes to think about those questions, and then we'll run the code block. I'll give it about another minute or so here. So remember, the two questions is first, what is going to be outputted to the screen? And secondly, what is this code block telling us about the variable x? Great, so it looks like most people got it. So yes, we will anticipate with x equal to 11 that it will display x is odd, and it's telling us if the integer or the number is even or odd, or if it's not an integer. So if we run this code cell now, we see it outputs x is odd. So now if we change this to something like 10, we'd expect it to output x is even because of this first case, and it does. But now this is what's nice about else. So if we input something else, so if we input something like 10.4, it should output something like x is not an integer. So that's kind of the nice thing about else, is it can catch all the other cases for something like this where we know that it's not an integer if it's not satisfying either of those two conditions. So just take a second here to talk about white space too. So see how the display is indented, a tab after the logical statement. That is very helpful because it's telling MATLAB, or it makes it easy to tell that this code is what happens after MATLAB checks this condition. Because if we didn't indent it like that, or all the way in, it's a lot more confusing and a lot harder to read than if we have it indented like that. And MATLAB will auto indent things like that for you as well, which is nice. So now we'll switch back to slides here and talk about lists. So lists are a way that we can contain lots of variables together and hold them in one spot. So a list is essentially just a collection of other variables. So MATLAB lists also start their indexing at 1, just like their strings. And you define a list by doing test list. So you have your variable name is equal to, and then you use square brackets, and you include all the different variables that you want in your list. And then if we want to extract data from a list, because usually if you're putting data into a list, you want to be able to somehow pull it back out, we can just do the list name and then parentheses in the index of, or the element that we want from the list. So like if we want the first element, we put 1 and that'll output A, or if we want like the fourth element, it'll output false. So lists are super helpful when you're trying to save a whole bunch of data values. For example, if you're doing a math model where you're looking at time series data and you're trying to generate your own time series data. So thinking back to the epidemic model example from last week, you could append the data each time or after each time step to a list. And then at the end of whatever code you have, you'd have a list with all the time series data that you could go plot. So this is why lists are very useful, because they help you hold data together in a systematic way. And just another note is that MATLAB lists cannot be negative indexed, because in some other languages, you could do like -1 to get the last element, but that does not work for MATLAB. So now we'll look at an example of a list. So here we're defining test list equal to this combination of different variables. So if we run this section, we see that it automatically converts all the variables, since the first one was a string, to strings. So now we have 4 different strings inside of our variable. And then we can see if we want to access, say, the 4th element, we just run test string of 4, and that'll output false. But just note, since there are only 4 things in the string, if we bump that up to 5 and rerun this, it'll error because there's not 5 things in our list. So when you are indexing lists, you have to be careful that you're not exceeding the number of elements in the list when you index it. But one other thing we'll note, because we're just about to use this, is if you do 2 integers, so say like 0, semicolon 9, and we run this, this will give us a list, or give us all the numbers between 0 and 9. And this is just useful because we'll be talking about looping here in a second, where we want to loop across a certain number of numbers. So just note, if you put the semicolon, we could do something like 100, and then run that again, and it'll put all the numbers 0 to 100. And this is just a nice tip to know, because if you do want to do something a certain number of times, you don't have to make a list where you type in each number 1 to 100. You can have MATLAB do that automatically for you. But now we'll switch back to the slides and go to for and while loops. So looping is when coding starts to get a little bit more interesting and a lot more useful. So there's 2 types of loops in MATLAB. There's for loops, which are going to loop over a fixed list of objects. And the general notation for a for loop is for object in a list, do something, and then we'll need an end statement. So we're going to do a quick example of a for loop before we go on to while loops, because for loops are pretty cool. So here's a basic for loop example. So this is the syntax. We have for, and then we have our variable I, and then the equals here is kind of like in. So for I in this range. So again, we're using that semicolon notation. So we have from 1 to the length of the test list, which remember we defined just up here to be this list, which has 4 elements. So the length function will return 4. So for I in the range 1 to 4, do something. And the something we're going to do is we're just going to print out that element of the list. So we're going to print out each element of the list. So when we run this code, we'll see that it outputs each element of the list just as we expected. And now we'll do another example here where we're doing accumulation. So this is where that adding like incrementing a variable will come into handy, because here we're defining total to equal total plus something. So that's kind of where that accumulation comes back in. So initially we have to define total to equal 0, and then we start our looping code. So here we have for I in the range 0 to 8. First, we're going to print out I, and then we're going to add I to total. So essentially, each time this runs, it'll continue to add the numbers up from 0 to 8. So if we run this code, it should output each number 0 to 8. And then note, we haven't displayed total yet, so then we'll need to display total so we can see if it actually worked. As you can see, it did, because it added up the numbers to 36. And adding up numbers through 0 to 8 isn't super interesting, but what's really cool about this is, say we want to add up way more numbers. So we can add up, I believe that's 100 million. So we want to add up the first, 10 million, the first 10 million numbers. We can run that, and it runs very quickly. Oops, I should have commented out display, because now it's going to try and print out all those numbers. So that's my mistake, because you don't want to print out 10 million numbers. So I'm going to stop the code before it crashes my browser. But you don't want to do that because it's printing it out too many times. But we'll give that a second to load while we talk about while loops. So while loops in MATLAB contain our will loop while a condition is true. So they're similar to for loops, but a little bit different. So the usual while loop notation is something like while condition, do something, and then end. So we can define whatever condition we want up here, and the while loop will continue until that condition is not true. And we need to note here is that you can accidentally make infinite loops with while loops, where it will never end if your condition is always true. And that's something you want to be careful of, because your code will continue to run forever, and you don't want that. So flipping back here, hopefully it's unfrozen. Give this a second. So this is a great example of why you don't want to do too much because here we're trying to print out 10 million numbers. So I'm going to just refresh the page so that it stops running that. This will take just a second to load. All right, so while it loads back in, we'll continue on with our presentation and then we'll come back to while loops. So the last big thing we're going to talk about is functions. So functions in MATLAB can be defined by a user. And we've already talked about some functions. So things like the round function, which is super useful, or things like string indexing and such have functions. So we can define our own functions if we want. And the syntax for that will be something like function, and then we'll have the outputs in a list that we want equals function name, and then the arguments that we want to feed into our function. So we could have anything going on after that. But in this example, this is just a super simple example. We're defining output 1 to equal something and output 2 to equal something else. And then we can have end. So we're not actually using our arguments here, but we will be using arguments in our code. So this is super useful because now you can define your own functions to do anything that you want to, and then call those functions without having to rewrite that code. So this lets you scale functions and do things repetitively, super easily, which is really nice. And also note that there's lots of functions that already exist in MATLAB. Like we mentioned, the round function that we have already used. So if you're thinking about writing a function, before you do it, be sure to look it up and see if it already exists, because there's lots of them out there, and Google will be your best friend for this as well, because a quick Google search will let you know what is already out there. So now switching back to our code, we'll hit new session, and we'll give this a second to load in. As it pulls back up our code here. So now we'll scroll back down and we'll start with while loops because we didn't quite get to those. Scroll down here. So recall that while loops have potential to create infinite loops. So here we have a while loop looping for some number of times until this condition is not true. So here we're going to try and do the same thing that we did with our first for loop, which was add up the numbers 1 to 8 before we changed it. So with this while loop, we want to add up the numbers 1 to 8. So we're going to loop while n is less than 9, but something is broken about our while loop here. So we increment total by n, and then we continue looping across that. So can anyone tell me what we're missing in this while loop, and why if we run this, it'll continue to run forever? Yes, so give it another few seconds here, but that is correct. We don't increment n. So the problem here is we define n equals 0, and then we're doing this while loop, but n is never being increased. So this while loop is going to continue forever because that condition is true. And we don't want to run this loop because, as we saw before, it could run or will run forever, and we don't want that because that will also probably make me have to reload the code, and that takes a second. So what we're missing is we need to increment n. So now we're increasing n by 1 each time. So if we run this cell, it won't go on forever. And then we can also print out the numbers. So if we run this section, it should print out the numbers 1 through 8. And then if we check the total, it's 36. So as you can see, there's multiple ways to do each loop. So we could use the for loop, or we could use a while loop to add up the numbers 1 through 8. Both work, but sometimes you want to use one instead of the other, depending on what you're actually looping across. So now if we comment out display n so it doesn't try and print everything out, and change this to a much larger number, we'll see when we run this section that it still happens pretty quickly. So it ran it just like that, adding up the numbers 1 to 1,000,000 in a blink of an eye. So now if we run that, we'll see that we've added up the numbers 1 to 1,000,000, and that's stored in total. So that's what's really nice about loops, is that they scale nicely. So if we're running something relatively simple, we can do that very quickly, countless times. So that's a lot nicer than having to do that by hand, which is a great advantage of the programming language. But now we'll talk about functions. So here's what we'll define a function. We'll start with this function, greatest common factor. So here we're just defining the greatest common factor of two numbers in a function. So we have x and y are our two functions. And then this is our block of code that is doing something to our inputs. So initially, we're going to define the variable greatest common factor. And remember that greatest common factor is what will be returned at the end. So here we use a for loop. So now we're kind of bringing it all together and using for loops and logical statements inside of our function. So we have for I in the range from 2 to x plus 1. So that's our variable value plus 1. We check some logical conditions. So we mod it x by I. And if that's 0, then I divides x. So we know that we'll then check y to make sure I also divides y. And if I also divides y, then we'll set greatest common factor equal to I. And then this will continue to loop over our range here until we've reached the end of our range. And this is nice because greatest common factor will be overridden every time a higher number is found. So then we can just return greatest common factor, and that'll be the greatest common factor of our two numbers. So now if we scroll up here, we can run a few of these. So if we run greatest common factor of 14 and 18, we see it outputs 2 very quickly. And then we can do bigger numbers like 225 and 42. And we'll run it and we see it gives out 3. And then we can do really big numbers like these numbers that I'm not going to try and read. And our function will scale to these. And it'll take a second to run here because remember it's looping that many times. And while this runs for a second, it should almost be done. But in the manner of saving time, we'll come down here and look at our next function. And then when we scroll back up, we'll see if it's finished. The next function we'll define is just a prime number checking function. So here, again, we have our list of outputs. So again, we're only outputting one thing. This time it's prime, which is going to be a Boolean variable. So kind of bringing back in everything. And then we have is prime of number x. So we're inputting x. So here, we initially set prime equal to true. And then we'll do this for loop. And again, we'll do if statements. So we can have for I in the range 2 to x to the 1/2. So essentially the square root of x plus 1. Because for prime numbers, you only have to check up to the square root, or to see if a number is prime, you only have to check the numbers up to the square root. And then we can just do a logical statement. And then if that number I is going to divide x, then we know that x is not prime because something divided into it. So then we'll set prime equal to 0. And remember that a 0 is equivalent to false. So if this function outputs 0, then we know it's false. And if it outputs 1, we know it's true. So now we'll scroll back up. And we'll run an is prime. So is prime of 7. We run that and we see it's true because 7 is prime. And then we do something like is prime of 9 and we would expect it to get false. And it does get false. And see how functions are nice because we can quickly plug in lots of different things. So now we want to plug in something larger. We'll just steal this number from up here. So plug in a very large number. And this might actually take a while to finish because prime factoring is relatively computationally expensive, so it does not want to paste. It's okay, we'll type in another number. So something like that, extremely large number, and then we run this section. We see that just like that, it actually happened very quickly, probably because something small divides into it, we get that it is not prime. So that's one really nice thing is that functions scale easily and you can use them over and over again without having to redefine anything. And if we just take a peek back up here, we see that the my greatest common factor has ran, and the answer is 1. So the greatest common factor of those two very large numbers ends up being 1. But if there's not any questions about functions, we'll switch back over to slides and talk about homework. But I'll give you guys a second to ask any questions before we switch back over. All right, great. We will switch back to the slides. So last thing we'll talk about is some homework. And remember, homework is optional, but it'll help you with learning MATLAB and also solidifying this stuff. So when the M3 does come around, you're ready to jump in on MATLAB and crank out some code for your math modeling problems. So the homework for MATLAB is to write a function that outputs the nth number of the Fibonacci sequence. And for those of you who don't know, the Fibonacci sequence is like the number 0, 1, 1, 2, 3, 5, 8, and so on. So the underlying pattern here is that the nth Fibonacci number is equal to the n-1 plus the n-2 Fibonacci number, or the next Fibonacci number is equal to the sum of the previous two. So your goal here is to write a function that when given an input, so for example, say you called your function Fibonacci underscore n, so say we put in 12, so we want the 12th Fibonacci, it would output the 12th Fibonacci number, which is 144. So that's the homework for next week. And also note, if you want to refer to anything, the code for all of today's stuff is available in the shared MATLAB drive. So if you want to go back and play with anything from today as well, you're welcome to do that. And that's strongly encouraged because the best way to get better at programming is to practice.
We're going to get started with the second half, which is kind of this problem solving session. Since last week, we looked at one of these previous M3C problems, the one on nicotine use. And, we started talking about, well, what assumptions do we want to make? I mean, even just what problem do we want to solve, right? So last week, we kind of did that problem analysis or the problem solving stuff. This week, what we're going to do is actually look at snippets of solutions that were submitted to the M3C for that same problem. And so these slides with these snippets, these are available in the shared kind of Google Drive where we're keeping all of these materials. Yeah, so let's go ahead and get started. So, right, as a refresher, right, what problem did we look at last week? Well, this was the M3C 2019 problem, and in particular, we looked at part 1, which was titled Darth Vapor, right? And so the problem statement was, often containing high doses of nicotine, vaping, inhalation of an aerosol created by vaporizing a liquid, is hooking a new generation that might otherwise have chosen not to use tobacco products. Build a mathematical model that predicts the spread of nicotine use due to vaping over the next 10 years. Analyze how the growth of this new form of nicotine use compares to that of cigarettes. Okay. And there is one piece of, so there was data that was also given for this problem, but then there is also this picture right here that shows the per capita number of cigarettes smoked per year for a bunch of years and has a few labels for some, I don't know, landmark events related to cigarette usage. Okay, right, but this was the problem that we looked at and we talked about last time. Build a mathematical model that predicts the spread of nicotine use due to vaping over the next 10 years. Okay. So what we're going to do first is we're going to kind of revisit a little about, what was talked about, kind of jog our memory a little bit before actually seeing what some other teams submitted. Okay. And so, right, a few of the questions that we kept asking, or how do I want to say this? Right. Yeah. So a few of the questions that came up were, what ideas do you just have in general, right? What ideas pop to mind as soon as you read the question? What approaches do you want to try? And of course, if you have a lot of experience, you've, studied or seen a bunch of different models, then, your mind might be jumping to a bunch of these. If you haven't seen a lot of models, that's totally fine. Right, but one of the first questions was, right, what some of our initial ideas were. And then, of course, what further questions did you have both about the problem and data, getting towards, what sort of, data would you like to have to start tackling this question, et cetera, as well as just, what assumptions were we starting to make about the problem? And kind of what all these pieces were getting at was we're trying to, start quantifying pieces of the problem so that we could actually treat it as something we can model mathematically. Okay. Okay. So some of the slides and kind of ideas that Keshav came up with. So, of course, we posed these questions, gave you some time to think about it and answer in chat. Keshav included ideas that he had come up with as well. The starting point was coming up with an initial problem definition, right? So, what does it mean to kind of quantitatively, study the spread of nicotine usage via vaping? So some initial, problem definitions, things that are, again, getting towards a quantification of all of this stuff is, right, well, what is the expected number or percentage of teens who vape over the next 10 years, right? Because there, in particular, here is something actually quantifiable, right? A percentage. Another idea, what is the minimum expected number or percentage of teens who vape over the next 10 years, right? And so maybe this is saying, well, sure, anything can happen, models may behave differently, but what is the baseline or this minimum number that we might expect? Otherwise, right, another approach is asking what is the expected number of vape pods used by teens over the next 10 years? And so, what's interesting about this third possible quantification is, right, now you're not necessarily asking, about kind of teens that are using. Well, okay, so what you're asking is something a little more, you might say, like economical, or right, something related to the economy, right? What is the total market share of vape pods that is possibly dominated by teen usage? So maybe the takeaway is, right, all three of these things are all getting at nicotine usage via vaping, but they're all getting at that in slightly different ways. Okay? Whatever your team comes up with, great. Use that initial problem definition, run with it, see what you can get. Maybe in the process of actually building a model and solving this question, you use all three problem definitions. Yeah, so this was kind of our starting point, trying to get at quantifying the problem, right? Okay, so what else did we kind of talk about? So we also started talking about what assumptions we might want to make about the problem and how kind of the population behaves, things like that. Again, getting towards quantifying things to actually build a mathematical model. So some of the things that Keisha mentioned were, right, well, one assumption we're going to make is that whenever we say teen or teenager, what we really mean is someone who's an 8th to 12th grader, okay? Which roughly corresponds to someone being 13 to 18 years old. So, certainly some 12-year-olds, I guess, are considered teenagers. 19-year-olds, I guess, are considered teenagers. But for the purposes of this problem, right, we're really specifying kind of, right, quantifiably, here's the population that we're interested in modeling and studying, okay? And sure, your model, you may, extend it to look at 12-year-olds, 19-year-olds. It's totally fine. It's your model. You can do what you want with it. This was our starting point for thinking about this question. Some other assumptions, right? Total number of teens is a constant and evenly divided among the 5 grades. And kind of our justification for that is, right, the population growth or change in population of the teenage population probably isn't going to change very much over the next 10 years. And so we could say, okay, well, take roughly this number of people in this age range, divide that number by 5 for 13 up to 18 years old, and then that's going to be how many people are in each population group. And again, that was just our way of starting to quantify things to build a model and answer this question. Okay. What else do we have? Assume that vaping refers only to nicotine-based vaping, and the kind of justification of this assumption is, right, well, the question is asking us to focus on nicotine use, okay? So, certainly, other things can be vaped, but to start at this problem, we're just gonna narrow our scope and focus on nicotine usage. If your team wanted to, you could look at, generalizations and ask, okay, well, what about other products that fit in with vaping? You're totally fine to do that. Just be sure that you answer, right, what happens with nicotine-based vaping first. And so another assumption that was made that kind of looking ahead, you might say is a little specific to a kind of model that you might want to try. But another assumption that was made was that the influence by a current vapor is the only way non-vapors decide to start vaping. And so the justification of that assumption is that peer pressure is known to be a major driver, and the fraction of people vaping based 100% on their own desire is likely small. So, sure, maybe someone sees, I don't know, an ad for some vaping product, and they're like, oh, that seems super cool, I'm gonna try it. Sure, that can happen. This assumption is saying, well, maybe it doesn't happen nearly enough or on the scale of the population that we care about to really impact, the results from our model. Okay, and that's totally fine. That's an assumption that we're making about our model, and so we're going to run with it. That's how we're deciding to quantify things. Okay, but these were just a few things that we came up with. Keshav talked about last week. Certainly there were other assumptions that were made that were great assumptions that didn't make it onto these slides. Your team and your model may have different assumptions. All of that is totally fine. It's your model. It is what you make of it. Okay. And so then the last bit that was discussed was just, what kind of model should we build? And so here, certainly you have a lot of freedom in what model you build and how you approach these problems. Some things that were mentioned, statistical models. So maybe you just take the data that is given to you, compute some lines of best fit, and then that's your model. It's perfectly valid. Another approach is this thing called an SIR model, which is usually used to model the spread of diseases. And so SIR models, they're something that we'll talk about in a few sessions if you're not already familiar with those. Another possibility is something like a probabilistic model, where you ask, hey, here's a population, what is the likelihood that someone will start vaping nicotine? So that's another approach you can take. Another thing that was thrown out are these agent-based models. But yeah, maybe the takeaway here is you have a lot of freedom for how you approach this problem, what models you want to build and develop. Really, it comes down to, whatever model you choose, develop it well, justify it, take it as far as you can get, but really, make it your own. Okay, so that's a very quick overview of the roughly hour-long session we had last week. Okay? So now let's get into kind of what'll be new for this week. So what we'll do the rest of this time is actually, as I mentioned earlier, actually look at solutions, or snippets of solutions that were submitted for this M3C competition, this problem, in particular part one. Okay? And so how we're breaking it up for the session is, first, we're gonna look at how some other teams went about discussing assumptions and how they justified them, if they justified them. After that, we'll look at a few of the different kinds of models that were submitted. And so I should say, 1 and 2, these are going to be snippets of larger solutions. So certainly a lot of context will be removed from these things. But the goal of these sessions is just to, give you a sense about, what more of a variety of some of these submissions look like. Afterwards, and kind of getting into homework, we'll have a few kind of case studies of, in quotes, full solutions. And I say, quotation full, because these are just part ones of, some other solutions that did fairly well. They didn't win the entire M3C, but they had some pretty solid approaches to part one. And so within these case studies, there are also 3 of the winners as well. And the homework is essentially, use some of the methodology and some of the questions that we're asking in these sessions to take a look at these submissions, see whatever you can notice, and just start getting ideas and whatever in mind for when you go to write and submit your submissions. Okay, so if any questions come up, feel free to use the Q&A. Otherwise, when I pose questions, feel free to post in chat, either to just the host and panelists or to everyone. You can see both, but otherwise, let's get started. Okay, so what we're looking at here are, again, snippets of assumptions that were made and written in kind of actual submissions to the 2019 M3C. One of these was from a lower scoring submission. One of them was from kind of a medium scoring one, and the other was from a higher scoring one. Okay, but the question, what I really want to focus on here is just what do you notice about each of these three? Right, what things jump out? How do they approach these assumptions, etc. So take a minute or two, skim each of these, maybe read some of the assumptions, read some of the justifications of them. Maybe another question to keep in mind is, when you're reading these assumptions, is there a sense on how these assumptions are necessary or might be used in their actual model, or how they might kind of go about modeling things? So let's take we'll say 2 minutes, read through these. Any observations that you have, feel free to post in chat. But otherwise, take a look and then we can chat a little about them. Okay, so we're getting some responses in chat so far, and so I can read what some of these are. So one of the responses is kind of in short formality. Bottom one, which I'm assuming this is the bottom one, uses abbreviations. Top one uses professional terms and is concise. The one on the right is elaborated on. But I can't help but feel that some of the assumptions are to the extreme. Okay. Another comment, the assumptions on the right are strongest because they are well justified and even include data at some points. Okay. So, great observations. One thing to note is that yes, on the right, certainly they bring in data to justify their assumptions, right? They're saying, here is something that we're going to assume about how the population behaves, right? Why would we possibly assume that? Well, here are a bunch of studies that say, here's why we should assume that, for example. Another comment was, right, some of these assumptions are to the extreme, and, certainly some of them may be. But the consideration is, what we're trying to get at with a lot of these assumptions is that, right, we're trying to narrow the scope of what we can actually answer and work with computationally and numerically, say. Right, so maybe, sometimes it's better to start with a narrower scope, see how your model does, and then expand the scope. Or you can say, if you can handle it, keep the scope a little more broad, but otherwise, yeah. Yeah, no, so great comments. Let's see. And you might notice that some of these assumptions, especially on the right, mimic some of what had been said before. Right, so maybe, right, for part 2, kids under grade 6 do not use e-cigarettes, right, is very similar to the one that Keshav made last week, saying, this is, right, 8th to 12th grade is the population that possibly uses e-cigs or e-cigarettes. And even, right, between kind of the one on the left and the one on the right, you might say that some of these assumptions are very similar. Yeah, just a few examples of what have been in some previous submissions. Okay. So let's take a look at some other assumptions. So this is a screenshot from another one. So maybe take a second, read through, and then comment on anything that jumps out, anything you notice. Do you agree with the assumptions? What further questions do you have, etc.? So feel free to post in chat any observations, any questions, any disagreements, any strong agreements you might have with any assumptions. So while we're waiting, so I can comment. So when I was reading this, right, so the first kind of assumption, or I guess definition, right, they say current drug use, we define current drug use as use of a given drug within the past month, 30 days. This definition is used throughout all sections of our paper. Sure. That's how they decide to define it. And so their justification is, well, it's the standard for current drug use for the National Youth Tobacco Survey, CDC, and other government agencies. Furthermore, survey data for use within the past 30 days is readily available. So maybe what happened was, this group was doing a bunch of research, trying to find what data they could find, et cetera. And they said, oh, well, here's how the CDC, National Youth Tobacco Survey, and these other groups just talk about data and things in this realm. And they have all of this awesome data that we want to use. So let's go ahead and kind of justify our use of that data by, making that our assumption that this is how we're defining drug use. Okay, and so one comment that came up in chat was, how do they determine that cigarette use will be at 3%? Is it supported anywhere? Right, and so this is in relation to kind of this assumption right here. Traditional cigarette use among high school students will not drop below 3%. Though teenage cigarette use is at a consistent downward trend for multiple decades, it is bounded because the percent cannot drop below 0. It is reasonable that the use will stabilize at some low percentage, because some students will continue to smoke cigarettes. We approximate the stabilization point to be around 3%, right? So the question is, how do they determine that 3%? That's a very, very good question. And so without further context and, looking at the full submission, we don't know if necessarily they include that as they have a reference for that, maybe if they discuss it later on. They mentioned we approximate the stabilization point to be around 3%. So maybe this is an artifact or a result of one of their models, how they decide to just model the use of, model the prevalence of smoking cigarettes. They said, well, here's the model we're going to use. Let time go on to, or take a limit. It's going to stabilize at 3%. And they said, well, here's the result. Let's just say that's an assumption. A priori, we don't know. So that would be, especially for kind of a judge, that would be a question to keep in mind looking through more of the submission, right? Because I would agree, this seems like a pretty bold assumption, and so I might want a little more information about this. And so part of why I mentioned, possibly it's further on, right? Because this last assumption that they make, right, magnitude of cigarette and vaping usage of high school is proportional to the magnitude of the growth of new nicotine users. Their justification is, well, look further on. We talk about this a bit more in depth in one of the sections, okay? So possibly that's what went into this 3%. Maybe they have data somewhere. Very good questions to hold on to as you kind of read further in this submission, okay? One other thing I want to highlight is that, right, they're making an assumption that high school e-cigarette usage will follow a relatively logistic model of growth. So already in kind of this assumption, or in these assumptions, they're saying, here's how we're going to model e-cigarette usage, okay? And so, sure, they give some justification for it, but kind of it was interesting, it jumped out to me that, kind of where they're introducing the model, part of it they describe in these assumptions. Okay. Okay, so those are some examples of, a variety of submissions and how they treated assumptions. Certainly, when you're making assumptions and using them in, whatever model you develop, do justify as much as possible. If you can have data and references that, help your justification, do incorporate those. But, right, do make assumptions, do tell, the readers what the scope of your model is and your report is, and then justify everything. Okay. Okay, so moving on. So what we're going to talk about now are kind of a few examples of some of the models that, that a few of the teams used in their write-ups, okay? And so, yeah, so some of what we'll see here are what I called interpolation. These might fit in with what was called statistical earlier on. But a bunch of people used a bunch of different ways to essentially model the curve or the trajectory of some quantity of interest, like the number of people using e-cigarettes, for example, or vaping. And they said, okay, well, using this line of best fit or whatever, here's what's going to happen later on. So a bunch of people use some sort of interpolation or statistical approach. Some people use more probabilistic models, and we'll see sort of an example of that. And then a bunch of people use kind of what we keep getting at are these SIR-based models, or when I say models for disease spread, except instead of, right, a disease, we're working with vape usage, say. Yeah, so let's take a look at kind of a few of these examples. Okay, so here are two snippets from solutions. So I'll give you a second to just look over, see some of the symbols that are used. If you don't recognize these symbols or don't recognize some of the underlying where these symbols might come from or what these ideas, where these ideas are coming from, it's totally fine. Again, these are snippets that have been, possibly taken out of context of a larger report. So we're not seeing the full picture, but again, maybe the goal here is to give you a few examples of what appears in some of these reports. Okay, so on the left, right, so we see a plot, right? We see a bunch of curves, a bunch of colors. What are the colors? Well, blue looks to be cigarette high schooler, red is cigarette adult, e-cigarette high schooler, and then e-cigarette adult. We look above that, right? We see a bit that says symbols used. So CHS means cigarette high school, CA, cigarette adult, etc. Right below this table, we see a bunch of equations. Okay, and so presumably CHS, that's going to be right high school students who use cigarettes. That's equal to this minus 2.05x plus 29.5. So, question for everyone, what does this x probably represent here? So feel free to post it in chat. What do they mean when they use x, or what does x represent? Would be your guess. Oh. Okay, so someone said time, probably, question mark. Another person said number of years past starting point. Okay. Yeah, so especially, here, this looks to be the equation of a line. Down here, we have, a bunch of data points and some straight lines. And then the x-axis down here is year, right? So presumably x is telling us something about the year. And if you plug in x equals 0, so CHS, plug in x equals 0, that's going to be 29.5. Look over here at this point, right, the CHS, which is cigarette high schooler, that looks to be probably about 29.5. So yeah, it looks like x is probably the number of years after 2011, right? And so what these lines are saying is, well, increase x, that's looking so many years after 2011, and then this goes out to about 2029. Okay, so the question that I want to pose now, and feel free to answer in chat, is, right, what are things that you notice about this plot? So what are things you notice about the blue line, which is cigarette usage for high schoolers? What about the red line? And then what about the green and yellow lines? Okay, so one comment is that the blue line, percent of high school cigarette users, hits 0, right? So follow the line at 2025, it's going to be 0. Right, if you were to plug in, so this is going to be about 14, right? If you plug in x equals 15, right, just using this equation, you're going to get a negative number. They've chosen to not plot below that, so they're actually capping it at 0, sure. Other comments, right, they incorporated already known data, right? So kind of these solid lines here. They've incorporated already known data as well as predicted data based on trends, right? And so the prediction is, right, they found the lines, the equations of lines that, you know, best fit the data that's given. And they said, okay, well, here's how we're going to model, right, the usage over time, just these lines of best fit. Another comment, so red and blue are decreasing and yellow and green are increasing, right? So, right, you can see that in these charts, right? In this chart, blue and red are going down, green and yellow are going up. Blue and red are cigarette usage, green and yellow are e-cigarette usage. And right, that's something that we can also directly see in these equations, right? The slope for cigarette in high school and adults, it's negative. Slope for e-cigarette usage in high schoolers and adults, positive. Okay. And yeah, blue and red, at least coming from this model, kind of the blue and red predictions tell us that, well, cigarette usage will go to 0. Yeah. Another comment is that the yellow line of best fit seems to be the least accurate. And so it's probably because the data it's derived from is more volatile, which is a very good observation. And that comes to kind of what these R² values are telling us. And so what an R² value is, how it, you know, relates to these lines of best fit, that's something that we'll talk about in a future session. So stay tuned. Okay. So I want to chat very, very briefly about kind of the one on the right. This was one example of a probabilistic model that showed up in one of these reports. And so if you've studied something about probability, and they also mention it, they use Bayes' theorem for something which predicts the value of a variable given you know, some known information. There's not much more I want to say about this beyond it appeared. Unfortunately, there wasn't a lot more explanation in this submission about kind of what the interpretation of this function f is, which was something that I was looking for when I was reading through these. But I just wanted to highlight that, you know, someone did submit something very probabilistic. Okay. Okay, so 2 more, right, kind of snapshots coming from different submissions. So and we can go a little more quickly through these. So the top one, right, table 1.4.2, what it seems to be looking at is something similar to the last one, right, where we were splitting up between vaping for high schoolers and adults, as well as cigarette usage for high schoolers and adults. Okay. And so, right, coming from their data, whatever data they used, you know, they computed these lines of best fit. And so at least kind of these first 2 rows right here, what they're doing is essentially the same as what was done over here, right? They took some data, computed these lines of best fit, right? Got these lines and then said, okay, what happens after a while? And so it's interesting that they have, you know, slightly different slope and whatever else. But anyways, what stood out to me with this submission was they said, well, here's one, you know, model we tried, finding a line of best fit. And then here's another model that we tried, something called a logistic curve. And they said, well, you know, for each of these models, for each of these populations, here's how these models do. Which, you know, reading through these submissions, it was really nice to, you know, see a team saying explicitly, we tried a bunch of things, here's how all of them worked. And then later on in the submission, they said, well, because this one worked a little better, this is the one that we're going to use going forward. Okay. But just another example of, you know, kind of what appears in some of these things, and especially what's nice to see as kind of a judge, especially triaging and looking through these and getting first impressions. Okay, and so then the other one I want to highlight is this one down here, right? So this is what we keep kind of alluding to. This is an example of an SIR model, or kind of a version of that, where we're saying, well, here are three populations, what they're calling potential users, active users, and recovered individuals. And what they're doing is they're setting up, so in this case, differential equations. If you want to, work with like finite time steps, we might call these difference equations. But what they're doing is, right, putting together a schematic and then the equations to say, well, right, what is the change in the number of potential users in one time step? Well, that's going to be proportional to how many active users there are, and then how many potential users there are. Okay, why this is a reasonable model for all this stuff, we'll kind of talk about in a later session. But this is another kind of model that appeared, and actually I think majority of the winning submissions for this problem use some version of an SIR, or I guess in this case a PSR model. Okay. Yeah. Okay. So I guess before moving on, are there any questions on any of the snippets of, I guess, either models or assumptions or anything else in these submissions that we've seen so far before moving on to some other models? Okay. Let's see. So one question in chat. So how would you use an SIR model to predict stuff? Would you simulate the model using code? Short answer is yes. You'd simulate it. You'd choose alpha and beta, plug in values, choose initial populations, and let it run. So yes, you would run a simulation, but this is all something that we'll cover, I think in 2 weeks in a later session. So stay tuned. Okay, so let's look at a few others. Okay, so here I have the questions actually written out. So these were two figures that appeared in the same submission, the same write-up. So take a look at these two figures. Questions I have for you are, right, what do you notice? What jumps out? Right, what questions do you have? And just a little more generally, what else would you have liked to have seen, or what things would you have liked to have been addressed in these figures or in the models that they're setting up here? So in particular, what do you notice and what jumps out about how they're approaching this model? Any thoughts? Any observations? Okay, so let's see. So first model doesn't look like a quadratic should be fitted to it. And the second model has a little bump around 1950. Right, so, okay, so the claim is maybe a quadratic doesn't go here, and the quadratic that's used here doesn't really fit, right, I guess what's happening with this bump. They're using previously known cigarette use as basis. Sure. Seems like figure one, it seems like they're assuming it's quadratic. When based on the data, could just as easily be linear or something else entirely. Yeah. Quadratic fit data doesn't seem to support the trend. There is an assumption that cigarettes smoked by year was 0 at some point and will be 0 at another point, okay, which is very much a bold assumption. Yeah, so a lot of comments here questioning the validity of using a quadratic to fit the data. And, you know, the rebuttal might be, well, sure, maybe it doesn't fit super well, but look how good our R² values are. Is that good? Maybe it's not. I don't know, but certainly. So another, you know, comment is, well, you know, nothing kind of in what's been indicated here or in the report was, right, what's happening in this case in 2010 or before, and what's happening in 2035 or after. I mean, certainly, you know, using this trend, you could say, well, it's going to be 0 after this point, or if you want to take that interpretation, it's going to be negative after this point. So maybe something I would have liked to have seen is, you know, maybe explicit mention that, you know, here is the range of years for which this model is valid. But certainly, yeah, a lot of people asking, you know, about the validity of using quadratic fit, which is a very, very good question. So another example I wanted to highlight is the following. Okay, so in the report, the team said, so using Desmos and data for the cigarettes bought per capita, which they assume to be cigarette smoked per capita. So this might be the assumption that every cigarette that's bought is smoked. We were able to develop a sinusoid with the equation, that's the equation, for years in this range. Yeah. And so then they have a few versions of these plots, right? So what questions do you have? What thoughts do you have about how they decided to interpolate the data using sinusoidal things? Do you agree? Do you disagree? What thoughts do you have on this approach? So maybe one question would be, right, so they say, so something I liked about this approach was they said, well, here's a range that this model is valid for. And especially if you want to, set up a model and predict usage later on, I mean, what's going to happen, over the next 20, 30, 50 years. So certainly one thing I had in mind was, well, if you tried to, go a little further, then because you're using a sinusoidal, fits. It's going to be periodic. And so in some capacity, your model's saying, well, it's going to just jump back up. Is that a valid assumption? Is that an aspect that they mention or directly address later on? Which again, this is just like a snippet of a larger solution. So maybe they address it, maybe they don't. But these are questions, especially skimming through, seeing the figures, getting a general sense of how they're approaching things. These are questions that I had when looking at this. Yeah. Okay. Cool. Okay. Okay, so now what we're going to do is we're going to look at another solution. Let's see. So I'll read through this one. As I read through it, keep in mind these questions. What do you notice? What questions do you have about their approach? And what would you have liked to have seen? We'll talk about it, and then I'll go. There's another example after this that I won't kind of talk about, but the slides are available, so do take a look. And I'll talk about some of the other kind of samples that we have. Okay, so this team's submission, and this was the entire submission for part 1. All right, so given that most vaping products contain large amounts of nicotine, and that determining an exact percentage of products that contain nicotine is unrealistic, our model represents the predicted trend of the percentage of Americans using e-cigarettes. In order to make our model as accurate as possible, we use only e-cigarette statistics, as e-cigarettes are defined as always containing nicotine. Okay, and so already that's an assumption that they're making. Our basic outline is as follows. Percent of Americans who use e-cigarettes equal usage trend plus pro e-cig marketing divided by anti-e-cig marketing minus government action, whereas usage trend is equal to 2.9, et cetera, times x to the 1.2, et cetera. Pro e-cig marketing is equal to 0.0216x plus 42340000. Anti-e-cig marketing, FDA equals, I'll just say this number times x plus this number. Government action is equal to 6.8 whatever times 45 divided by 23 times x. The equation is divided by 10 to ensure the result is a percentage. It is important to note the amount spent by e-cig companies is in millions, while the FDA spending is in thousands. X is the number of years after 2019. Compiled together, the final equation is this whole thing. Let's see, and then they have a plot. It says years after 2019, and they're showing percentage of Americans who use e-cigarettes. The area under the graph, the integral over the interval x equals 0 up to about 5.5 years after 2019 would be about 5.5 years into the projection and show us the peak number of e-cigarette users in the US before the number of users begins to decrease. Right, so what observations do you have? What questions do you have? What do you notice? What would you have liked to have seen? Yeah, please post in chat any observations, any questions you have about this. Don't be shy. What observations, what questions, what would you have liked to have seen? Okay, so some comments. So government action seems a little vague. I'm wondering how they came up with that number, which is a very, very good point. And I had the exact same question, right? All of the numbers that they use, right? I mean, you know, for pro e-sig marketing, anti e-sig marketing, as written, they're using linear models, right? Presumably lines of best fit for something. What they are fitting is not at all clear, to me, at least coming from this. Usage trend, looking at how they've written it, they're using some sort of power law or power model, you might say. How they're getting these numbers, not at all clear. So certainly, right, where these numbers are coming from are one big question I've had. Someone else would have liked to have seen the graphs presenting years before 2019 to get the greater picture of what is happening. Sure. You know, kind of how is the data being used, where are things coming from, consideration of the anti ads or the anti e-sig marketing made it more complex, which, you know, certainly, yes, it's a more complex model. If that's the model you want to develop and you're comfortable with it and you can justify it, then, you know, go with it. Great, see what you can get. But certainly it is a bit of a more complex aspect. Someone found it interesting how their approach was from an economical standpoint. So that was something that stood out to me as well. You know, they really tried to incorporate something about marketing, and it seemed like these quantities were amounts being spent. Another question, aren't anti-e-sig and government action the same thing? Possibly. And so maybe they decided to keep things separate for some reasons that aren't fully explained in this. But yeah, so great observations, asking excellent questions. All the same questions I had when looking at this. Yeah, so maybe the takeaway here is, you know, sure, you can have a very complex model. You can be incredibly creative with how you approach things. Just, you know, justify it and explain it in a way so that maybe some of these questions that a judge or someone else reading this might have, they don't have as many of those questions. You know, yeah, okay. So there's another example that's similar. Same questions. This was the entire part one for one of these submissions. The slides are available in our shared drive. So, you know, treat this exercise, this one as homework. And so in the last few minutes, I wanted to actually mention kind of the other homework. So, right, when you're looking at these submissions, either, you know, some of the winning submissions or some of the non-winning submissions, you know, when you're looking through these, think about how a judge or someone who's, you know, looking through these submissions to try to decide, you know, which ones, I don't know, seem like they have a good approach and can have a good answer versus, you know, all the rest. Guiding questions to ask are, you know, is it easy to figure out what the assumptions are? Do they make it easy to, or do they actually justify them, et cetera? Is it easy to find what the model is? You know, and this might be, do they have enough figures and charts that illustrate what they're doing? Is it easy to find any equations, kind of describing what they're doing, et cetera? Things we didn't talk a whole lot about here, but we will talk about later, are kind of pros and cons, and you might say, kind of getting towards, like, it's not really a sensitivity analysis, but do they discuss, you know, ways that their model is, or things that their model is especially good at? Do they discuss, you know, shortcomings or other things that their model could be improved on, maybe if they had more time or more data, et cetera? And so maybe how transparent are they about, you know, how good their model is? And just in general, keep an eye out for things that you especially like. Do you like how they've formatted tables and the kinds of things they've included in tables? Do you like how they use captions for figures and like legends, things like that? Because then certainly when you go to like compete and write up your own solution, maybe copy some of the things that you especially like and some of the formatting and some of the ways that teams, actually went about their solutions. Emulate those things in your own submissions. Okay. Okay, and so it is top of the hour. So what I'll do quickly is for the homework, so samples available here. These are in the shared folder with kind of all the slides and everything. And if you go to the M3C 2019 samples, samples 1 through 3, they're samples that are their submissions that did fairly well but weren't winners. 4, 5, and 6 are winners, but I've just included kind of part 1 of their solutions. So part of the homework is take a look at some of these solutions or submissions, see what you like, see what you would have liked to, right, just ask what questions you have, what do you like, what could have been improved, do you think, etc. See the variety of ways that people approach these things, the kinds of charts that they use and figures, etc. Do they talk about strengths and weaknesses of their model, things like that. But these samples are all in this folder. So, over the next week, if you have an hour, even half an hour, take a look, skim through, see what you like, see what you don't like. Just ask these questions and start kind of formulating in your mind, what a well-written submission, and a well-justified model, what that looks like. Because that'll certainly go a long way in, writing your own submissions for these competitions. Okay, and so with that, we'll go ahead and end. So thank you all for hanging around and looking through a few of these submissions with us. Next week, we will start off by looking at MATLAB again, but then the focus will be on kind of data analysis in MATLAB and starting to look at data. And then we'll look at another M3C problem and do that sort of problem analysis. And yeah, so with that, thank you all. The links have been posted in chats, and we'll see you all next week.